Okay, excellent. Thank you, everyone, for coming here. I hope you had a good long weekend. Wajira, did you receive your suitcase?
Yeah.
Okay. I'd like to everyone to welcome Wajira, who's a new member of this class here. She's been attending many previous sessions via video, but has finally arrived here in person, and as has thankfully her luggage, which is really good. Okay, so ladies and gentlemen, today we have a rather aggressive agenda, and this agenda will likely follow us through much of the week. This agenda focuses at a very high level on the notion of monads and monadic composition, but the particular application of that we're going to be talking about for much of today is this management of state information in a functional context. And this relates to chapter 6 of this book, Functional Programming in Scala. I consider this chapter, of all that we're going to be going through as required readings for this course, this chapter to be the most challenging conceptually in terms of what's going on. And I'm appreciative if you've studied it carefully. As you'll notice through my annotations of this book, you're not alone in studying it carefully. And I'd like to be able to use this week to make sure that those in the class have a pretty solid grounding on what's being discussed and its relations to other things that we have seen in this class and that will play big roles within the coming weeks when we're talking about Spark. Okay, so this chapter, chapter 6, talks about this management of state in a functional context, and it makes the point that state-based programming that updates states is not inherently in tension with or in contrast to functional programming that eschews side effects. The two are compatible. One can, using a functional paradigm, implement support for updating state. But we do so in a way that is more explicit. So, much of what follows us through this chapter is similar to what we've seen in previous chapters, where when we have a functional situation, rather than updating something in place, rather than mutating something, performing a side effect, we use different words to describe this phenomena where we have some aspect of state and we change it, say, within a method. And it's not something we return, it's just something updated by the method. Rather than pursuing things in that way, instead here we update it by returning it as a value. So we still have functions which take in clear arguments and which return factors, and the function has a clear job in that it takes some inputs and returns some well-defined outputs. And it uses that standard functional mechanism, input parameters and return values, to implement an abstraction of state, a representation of these values which change over time. And a central means of accomplishing this is this notion of a state transition or action or transformation. And I have some disagreements with the chapter in terms of the notation I would have used or the terms I would have used for things. So within this chapter, I thought it's actually extremely well done. But they make what is, in my in my view, the unfortunate choice of calling a state action or transformation or transition or mapping. They end up calling it a state. And the authors warn, here state is short for computation that carries some state along, or state action, state transition, even statement. But they use the term state for it. And it's extremely important for the sake of understanding what's going on that you not simply view this as the current state, but as a mapping of states, as a sort of computation, as it were. So it's a state transition we're going to be talking about. And rather than calling it state, I'd probably call it state transition or statement or what have you. What we're going to see as a key component of this is this notion of chaining computations together. Taking one computation and another one and linking them up, or as we would say, composing them. So one takes place before the next. And the key component for all of this is the unlikely, neglected stepchild, perhaps, of our earlier work with functional programming, FlatMap. FlatMap was something that one could excuse if you viewed as kind of a weird variant of map. But in fact, it turned to be central to the drama of chaining together state transitions on the one hand, and by extension, or more broadly, the notion of chaining together monads. These monads which capture metadata or state together with a value. And it turns out FlatMap will be really, really useful as a sequencer. It's going to be central in this whole role of composition. It's composition of this action with this one, so that one occurs before the other. Without it, there's not really a notion in functional programming that one of those computations would have to occur first. But when we sequence them together, there's an ordering accomplished because data dependencies, because the second one will depend on the value of the first one. It turns out FlatMap will also aid in cleaning up the syntax. Well, that's a bit of and just like that, going from this to that. Okay, I didn't mean to advance it, and I'm wondering actually if with the slideshow there's actually there it is. The fox has shown its tail. Okay, now we're back here to this, but the point is that we can use FlatMap by virtue of Scala's syntax with 4 comprehensions. The fact that we're using FlatMap actually allows us to really clean up the syntax. A very nice composition of actions in a way that's quite clean syntactically, how we phrase it. We also see that the author argues, I think somewhat persuasively, that that the functional programming we see here and imperative programming can be used side by side. Okay, so FlatMap is going to be central to our goals here. And we're going to see how we can use it to implement the functionality associated with these state transitions, what is unfortunately called state within the chapter. Okay? So, as I say, it's easy to fall prey to a misunderstanding that FlatMap is kind of a curious little additional item that's rarely used to kind of flatten the kind of nested lists that come from places. Just to recall that notion of FlatMap, and maybe we'll go and call up our Scala console. Where is my Scala console? Oh, okay. No, it's not that one. Here we go. Here's Scala. Okay. I posted, ladies and gentlemen, over the weekend, the transcripts from previous sessions, and you enjoy recourse to them even now. So I was sort of futzing around here. Okay, so ladies and gentlemen, let's think about a use of FlatMap. In order to do this, I'm going to terminate Scala, and don't worry, I'll come back to it. Hey, come on. Okay, here we go. Quit. Hey, come on. Okay, here we go. And I will just point out that I'm going to use this in this place with a thing called document.txt. Does anyone remember that document?
That's Stone's thesis, right?
Yeah, exactly. Exactly. Do you remember that? I had you download it earlier, and I'd invite you to go find where it is and to invoke the Scala tool from that location. Okay? And we are benefited now, ladies and gentlemen, by many weeks of experience with Scala. So that puzzlement, which seemed so challenging on that first day of class here, hopefully will start in many pieces will start to fall into place for what we were manipulating. We're going to go revisit that original example wherein we used flat map, ladies and gentlemen, okay? So I don't know if people remember us on that first day, what we did. What did we do roughly?
We took the document in.
Yeah?
We then split it into, we got the lines of it, and then for each line we split them into words.
That's right.
And we used flat map to do that because otherwise we would have gotten a different collection back for every line
Good.
instead of for the entire document, and then we started
Good.
counting different things about it.
Okay,
And
good.
some kind of-
So let's go see this kind of traditional use of flat map. So, ladies and gentlemen, we are going to go here, so we're going to import scala.io. Lots of things in scala.io, okay? And we're going to say source dot from file. Scott, your memory is very good. That's great. Scott.
Well, the reason is because I asked a question specifically about map versus flat map.
Exactly.
And it was basically what we said was that flat map returns a monad of the same type it takes in. Correct?
Yes,
And
that's
so
correct.
it's
The same type on which it has been invoked.
Right.
Yeah.
And so you can pass the monadic information, the metadata, I believe, along the chain.
Yes,
I
that
think
is
was what
that
we
is
were
true.
discussing.
That is true. So, ladies and gentlemen, do you remember this source from file? This now, what is this thing here? Does anyone recognize that?
It's an ISO standard. I don't know which one it is.
Yeah, basically it's a standard around text encoding. Okay, so it's basically allowing us to understand the character set involved in that particular document, and this gives back an iterator. Okay.
So from files is curried.
And if we said .make string, it would actually present here, .make string, .mk string.
Nice.
Okay. Okay. Now, what I would like to do now is, since this is an iterator, I'd like to say get lines on it. Okay. And then, ladies and gentlemen, I'd like to say to stream. So what do you think I'll get out of this now? If I pressed enter, what would I see?
Each
Virtually
element is going to
nothing.
be a line. Each
You'll
element
get,
of the
you'll
screen.
get a stream of lines, but you won't see anything except for the first line because it's
You only see the first one. That's correct. So if I want to see the first 5 of them, how would I see it?
Get 5 force. Take 5 force.
Yeah, okay, good. Take 5 and then force. Okay? So here are the first 5, right? Good. Incidentally, suppose I were to just say this again, what would I see?
No, you'd see the first five because they're
I'd see
all-
the first 5 because, mumble.
Really?
Okay,
Did you source it again?
mumble. Oh, I sourced it again. I created it again. Yeah, quite right. Yeah, indeed. I sort of recreated it
So if
rather
we
than.
said val something equals
Exactly.
that, and then we indeed
Yeah,
put it
yeah.
up
Let's
there.
try that. Let's try that. It's a fine notion, ladies and gentlemen. Suppose we had said this. Well, let's do it
Whatever
step
you
by
wanna
step. Val.
source,
Sorry.
S.
You know.
You know,
Sorry?
one of the things that this textbook said
Golden
was that
Graham.
using short names is beneficial. I don't know if you breezed over that part or if you.
No, I've
answered that with the
been,
red name.
I've been pondering that. I've been pondering that. You'll notice that I've alternating between different impulses. I'm having a civil war in my head.
Funny, we're actually running the
Okay.
style guide for 70 class right now.
Okay, so ladies and gentlemen, thesis stream here. Okay, here's the stream. This is a stream of what? Whence did this come? It's a stream of,
Lines.
indeed, lines, ladies and gentlemen. Okay, so here, if I say dot take 5 dot force, what will I see? First 5 lines. There they are in succession. And now suppose I were to say thesis stream again.
You should see the first 5.
There I'll see the first 5. Why? Why are they there?
Because they've already been calculated.
They've already been calculated. They're already
They're
cached.
yeah.
They're
Now,
they're
if you-
memoized.
If you call take 5 again,
So-
will it get the next 5 or will it get the same 5?
That's a good question. I think it will just do take 5. It'll just do the first 5, but I could be wrong. Watch this. It's still just the same ones.
Okay.
Yeah, yeah. Because this still refers to the head. So
Unless you drop.
yeah, exactly. You could drop and then take more. Yeah, yeah. Or you could take 10. Okay.
Okay, I was just wondering, 'cause I'm still trying to figure out how that
Yeah,
works.
yeah. In fact, there was a famous jazz piece from the 1950s called "Take 5." I think that maybe I don't think it is some stuff. Take 10. Okay. Okay. So, ladies and gentlemen, so here we have this. We have 2 streams. These are the lines. Now we're going to ladies and gentlemen, we are going to take each of those lines and we're going to split them according to word boundaries. So anything that's not a letter, ladies and gentlemen, we're going to use as a separator between words. Are we ready for this? Okay, now I'm going to do this deliberately in a fashion that's going to prove problematic. So for each of those lines, I'm going to map over those lines.
Could you not maximize the screen?
Oh,
We're bottom left and right. We don't.
oh,
It
oh,
cuts off.
oh, that's most peculiar. Okay.
Most projectors these days do it.
Yeah.
I don't know why. Just drag it up from the
Do you-
bottom.
It has to do with
No.
TV versus monitor projection, I believe.
Okay.
Yeah, I noticed it on my TV too. I don't know why it crops it like that. That's perfect.
Okay. Is that okay?
Yeah, it's perfect.
Okay, ladies and gentlemen, for each of those, we are going to split it. So tell me, if I want to take each of those things, here is a what? Is it an int? Is it a person?
String.
It's a string, indeed. So how would I say split the string? I'll tell you. This is
Underscore dot split.
okay. Underscore dot split. Okay. Yep.
Okay.
Okay. And I'm going to treat it as a raw string. Alternatively, instead of doing raw, what could I have indicated?
Triple quotes.
Triple
right?
quotes, indeed.
Because you're going to do a general, I'm sorry, regular expression.
A regular expression here, ladies and gentlemen. A through Z. A through Z. So basically, this is saying anything that's not one of, one of A through Z is either lower as lowercase or uppercase letters, I am going to split on. And actually, it's going to be a sequence of one or more of them. Whenever I see that, I'm going to split on it. What will I see? What do you think I'll see out of that?
You'll get a collection of
Sorry.
strings.
A collection of, okay, good. So let's watch this. Okay.
Well, of course you're not gonna-
Okay. It would be nice if I could see it. So, okay, ladies and gentlemen, one of the things I'm going to do here is instead of, just so I can see it more clearly, it's nice that we're doing it as a stream. I like streams. But I'm going to say to array, okay? What would I see there? Scott articulated it earlier. This is what I'd see. Why do I see that? Here's the stream. Well, okay, let me just do it without the map. And you're going to tell me why do I see one from the other. So here it is before the map that does the split. And here it is after the map. What's going on here?
Each subarray was a previous single sentence, so the split generates The split itself generates
That's
an
right.
array.
The split itself generates an array. What commonalities are shared by these words? What's their defining thing? Why are they all in an array together?
They came from the same sentence.
Came from the same
From the
line.
same line.
Same line, right? They were all in the same line together, right? The design and use of a smartphone data, right? And then here, collection tool and accompanying configuration. See that? Okay. So, ladies and gentlemen, we have an array within an array. And so that isn't what we wanted. We wanted to turn it into words, the whole long array of words, and instead we got an array of arrays. So what do we use instead of map?
Flat map.
Flat map indeed. Here's flat map to the rescue as kind of what might look like a bit of a hack. Okay, so we just flattened it. Now, instead of having this, we instead have this. Okay, let's compare that. So this is with map, boom, and this is with flat map, boom. Okay. Okay, here we are. The design and use of a smartphone data, the design and use of a smartphone data collection tool. You notice it's flattened it, right? These internal arrays have been flattened out. It's linearized it, right? Okay.
Alternately, you can say that it performs its function on the contents without actually changing its container.
Yeah, you could say something like that.
I don't know if that's correct, but that's what it looks like.
Yeah. Okay, so ladies and gentlemen, here we have a sort of traditional use of flat map. Okay, in both map and flat map, we're going over each of the lines, but in flat map's case, what's going on is that it's returning, ladies and gentlemen, instead of going for each line independently and returning an array, it's instead going for each line, and it is returning something that gets knitted together into one long array, right? So each line here yielded an array. Each line here gets sequenced together with the other items. It is sequenced together with the lines before it. So this flat map has actually knitted together the values that came before it with what came from each particular line. A particular line yielded an array, but that array got meshed with the other arrays by being placed one after the other. It got sequenced there. It got composed with the other arrays. And we're going to see that same composition, that same sort of placement of one thing after the other is going to occur when we're dealing with functions as well. Yes, Kurt?
So does flat map just do an extra step for map? Or does it do it differently? Does it do a map and then a flatten? Or does it do some other process?
It's some other process. It's actually, flat map itself, as we'll see, knows how to compose together the value on which it's called and the value that's returned by it. It's going to be something which is going to be central to our use of it on functions. Here, it's going. What flat map is doing is it's knitting together the values obtained from each separate line into a long sequence. Okay, so this is going to be key for our use. Yes.
I'm just writing this.
Okay. Okay. So, ladies and gentlemen, flat map is going to be a key sequencing operation that opens up a huge potential functionality using what are called monads. Okay, it allows us to compose successive actions in a very general way, and supports easy definitions of other methods. Okay, it allows us to define methods in terms of flat map, and it permits custom sequencing. So I'd like to talk about flat map in its use. Okay. So flat map is written variously in functional languages with signatures. It can be written most commonly this way. So what do we see here? Can anyone describe, if I describe this as a function, what does that function take as an argument?
It takes a monad of type A.
Okay.
And a function that takes in A and yields a monad of B.
Okay.
And it yields a monad of B.
Okay, so ladies and gentlemen, flat map itself is a function, and it's a function mapping from this pair of things. This X means it's kind of a pair of them. Okay, it's this thing and that thing. So it's a monad and a function. Taking those in, it returns a monad. Okay. Now this monad, for our case, for most of the discussion here, is going to be this thing called state, or we're going to be more specific yet, because I want you to think in concrete terms. Rand of int. Okay, rand of int, ladies and gentlemen, which is defined on page 84 of your book. Okay, is going to represent sort of randomizing action, an action that uses random numbers. Rand of int. Okay. It's going to be something which takes in a random number generator, and having that taken in, it returns the result of a calculation that uses that random number generator, namely a value and a random number generator. Okay. Okay, ladies and gentlemen. So here, we're going to be applying it in Scala. When we apply flat map in Scala, take a look at this. When we apply flat map in Scala, we're applying it with a different syntax. Tell me, those in the room, where is this one here? You notice we're passing it. We're passing it explicitly, this thing here.
It's the stuff that comes before the dot.
This is a function. So yeah, where is this MA? It's the thing that comes before the dot. It's the thing on which we're calling it. That's basically this.
So,
Okay?
so can you call flat map on any monad?
Yes, you can call flat map on any monad. I mean, it goes by the name bind often, but yes, in Scala it's consistently called flat map.
I'm just curious, because I'm kind of trying to figure out, how would I know what's a monad?
Well, a monad we're going to be talking about later, but it provides two operators. One is called unit and one is called bind. In Scala, the way of phrasing bind is always consistently flat map. So it has a flat map operator. Now, that isn't the only thing. The presence of those methods is not the only thing that defines a monad.
Right.
It has to obey certain monadic laws as well, but we'll come to that later. Okay? Okay, so ladies and gentlemen, here's, if we're dealing with Scala, typically we're calling flat map on MA. We're saying MA dot flat map. Okay? Just like we did here. We said this thing dot flat map. Okay? This whole thing, the result of this computation is this MA here. Okay, this monad. Okay?
And in our case, M is array.
M is an array. M is an array. Yeah. Because we rendered it into an array. Okay, now let's talk about a couple of features of this. Okay? So the first is that flat map, like map, returns something here that's a monad of the same type. So if I call map on an array, what do I get out?
An array.
An array. If I call flat map on an array, what do I get out?
Array.
Array. Now, it could be an array of a different type of element. So if I call map on an array of ints, could I get an array of doubles out?
Sure.
You bet I could. Here, let's do it.
Divide by
Import Scala.math. What's that?
Just divide it by 2.
Oh, no.
Sure.
Yeah, or let's import Scala.math. Ladies and gentlemen, if I do array of 1.0, 2.0, 2.
You want double.
7,
you want
1.
ints there, right?
Sorry?
You want ints there, right?
I want
Ints, I thought, never mind.
3.14159. And if I did dot map, oh, of course, sorry. I see what Kurt was saying. Yes, of course. Well, okay,
You can go
sure,
the other way.
we'll start with
It's
this. Okay, ladies and gentlemen, if I wanted to do,
Floor or something.
yeah, exactly, floor, but I don't remember, yes, okay.
2 int. Just,
Yeah, okay, sure, that's good. Dot 2 int. What will this produce?
1, 2,
3.
2, 3.
Okay, good. Ladies and gentlemen, here we map yielded a type out that's different than the type on which it was invoked in terms of the elements, but in both cases they're an array, right? If you apply map to a collection of a certain type, you're going to get a collection of that same basic type, but the elements may be of a different type, right? Similar with flat map, ladies and gentlemen. Now, if I tried to do this with flat map,
It'll complain.
what will happen?
You're not giving it a function that leads to MB.
Exactly. So, why is it unhappy? Why will it be unhappy?
Because you're giving it the wrong input.
Give it the wrong input. It says, look, found something here, there was an int, but it actually needs a collection, okay? Okay, fine. So I could say, maybe what I want to do here is I want to provide it with an
Give it a
array.
Square root or something.
An array of, let's do it. Let's have it take in a value x and have an array of x dot 2 int and then x plus 0.5 dot 2 int. Okay, what do you think will happen then?
Should work.
What will I get out? What's going on
It
here?
doesn't keep the returns separate.
Well, yeah, let's try that with map. Let's see. Could I do that with map?
Sure, it would just give you.
What would it say? It'll give me
Yeah.
tuples. What does flat map do? It flattens the tuples. Right? This is flat, and it's sequencing those tuples that are returned. Okay. Okay, ladies and gentlemen. Let's talk though about how we're going to use flat map in our case. The point is we're going to be calling it on MA as MA dot, Monad dot flat map of this thing, and it's going to return back something that's of the same general type. Now, how is flat map going to apply in this case? Well, there's going to be several pieces to it. Okay. Flat map is going to be called on this monad, and the argument to flat map is going to actually indicate what to do next. Given the value that's in here, what do we do with it? Okay, and this what do we do with it is itself going to return a monad. Okay, and as a result of that, performing this function on this value, we're going to return a monad too.
So this is effectively taking in a monad, unwrapping it to get the value, applying it
Yes.
to get the other monad, rewrap it, and spit it
Correct. And potentially combining or sequencing these two. Yes, that's correct. Yes, that's
out. I
right.
mean, I'm just.
Or it's actually not so much sequencing these two. That's what's implicit in here. Yes.
Okay.
Yes, it's taking taking the value, unwrapping this value, creating a monad from it, and returning monad. Yes.
Maybe it would be helpful for us to think about what that would look like if instead of flat map it were map.
Sure.
So in map, the difference for the signature is just instead of MB, it gives you B, right? From A to MB. It would
Yeah.
give you A to B instead.
It'll be A to B instead.
But if you gave map
That's correct.
an A to MB,
Yes.
and the output would be MMB.
That's correct. Yes. MMB. And that's why we're seeing that here. When we gave map this thing, we're going to actually get out these nested structures, right? Okay, so ladies and gentlemen, let's think about this. Let's try this a bit here. So, we're considering this here. Let's try it with a simple example that we're familiar with. So I'm going to create val v1, and this is going to be sum 3. And value v2 is going to be none. What are these values? There are what? Instances of what?
Options?
Option, yeah. And this is option of what? Well, it's int, exactly. Indeed. Okay, ladies and gentlemen, if I say I want to do a, if I want to do here dot map of x to x square, what am I going to get out?
Some
Sum 9.
Sum of 9. That's right.
But now it's an option instead of a sum.
Well, it's sum of 9. It's of type option.
But what's
Right?
interesting, I think what Kurt's getting at is that the value is sum of int, whereas this is now an option of int once you map it.
Yeah, this is just a subtype of option. It turns
Okay,
out.
I'm
So
not sure if
it's
that's too deep.
yeah, it's an interesting point, and it's because I explicitly specified this, and this is a subclass of option. It's specified it that way, but that's not something too much to worry about. Okay, ladies and gentlemen, could I do that with flat map?
I don't think so.
No. What would happen if I did that with flat map?
Well, you're not. It's going to error.
It's going to give me an error because it says, hey, this needs to return a what?
In other words, flat map accepts those inputs that are flattable.
It's not so much that. So, ladies and gentlemen, let's try this. Let's do this with another item. Let's suppose that we had, instead of x times this, suppose that we said x divided by x. Okay? What am I going to get out?
You're still doing the same issue.
Okay, sorry. I meant to do map. What am I going to get out with map?
Yeah, sum
Sum
1.
of.
Yeah.
Okay, good, because this is a 3. So,
Flat map would be helpful if we're adding sums together.
well, yes, that's true, but watch this. Suppose I did this. What would I get out?
Errors?
Yes.
Get out an error, right?
Yeah.
Right?
Mhm.
Why is that?
So it is divided by 0 is undefined.
Okay, that's right. Okay. Suppose I were to do the following instead. So that's because this is treating it as a number, right? Could I say here, try this dot to option?
No, because it's Oh, you could, but it'll give you something nested, I think.
Yeah. Okay. Import
So,
Scala dot util dot. Okay. So if I did this, what would I get?
Something nested, I think. Some yeah.
very nice.
Sum of none. And suppose I did it on sum of 1. Ooh. I get sum of 1, right? What's going on there?
Well, it's nesting it because it's a map.
It's a map, ladies and I want to indicate somehow that I want it to be robust so that if this thing is 0, this thing won't cause a problem. And it seems to almost work, right? If I do it with this, it correctly handles it. At least I don't get an exception anymore from this, right? If I do it with 0, right?
Mm-hmm.
Sum of 0, at least I don't get an exception anymore. It's not bombing out. So that idea of having a nice robust pipeline that can handle errors, so important in big data to be able to handle missing values and aberrant values. So we're part of the way there, but I get this weird construct out, sum of none. And then if I do it on something where no error occurs, what do I get out?
Sum of one.
Sum of one. Oh, but that's not what I want. I want to flatten it. What do I call instead of map?
You want to flatten it, so
That's right. Who are you going to call?
flatten it.
Flat map. Indeed, ladies and gentlemen. So here we go. And now suppose,
None.
none. Okay. Now we're cooking with gas, ladies and gentlemen.
Because try the monad?
Try as a monad. Yeah, in fact,
So since
I made a mistake, and I realized it fairly quickly. Let's do this. Let's do this. Okay, so instead of doing options, let's do this. Okay, success of 1. Here, try with 0. Okay, so here it's actually returning, okay, that it got a failure as a value. This is not an exception, ladies and gentlemen. This is a value. It knows that it failed, okay? We could do it with this. This is a monad too. Try. Oh, it's a thing of beauty, isn't it?
Oh, okay.
Yeah, look at that. No, the internet readers could be excused for watching line dividing this by itself. It's just to simplify the example. Okay, ladies and gentlemen, if I did it with 0, it would indicate that, but that's a real value. It's not an exception. I can handle it. I could say dot map of x to x squared, right? I could do this, and it's going to give me a nice value there, and this is going to go all the way through. This goes all the way through, which just propagates because this failed. It has a failure, and so it's going to just go through here and propagate a failure. This true is a monad. This too is a monad. Ladies and gentlemen, so here this flat map provides us with a way of indicating a computation that can fail, and that was one of, you may recall, earlier in this book, that was one of the places that the author talked about when he was talking about the option data type. On page 55, he comments, flat map is similar to map, except that the function we provide to transform the result can itself fail. Do you see what I'm saying by fail? This thing can fail here. It's not just that we can have a failure passed in the first place, something that was no good in the first place passed in, like something like this, on which we call flat map, but rather we could also have a failure along the way in this computation. And we achieve that by calling flat map, right? If we tried calling map, remember what happened? If we just did map, what again would happen? What would happen if we tried map here?
That would just be none.
Okay.
Oh, sorry, the try failed.
It's a try of try, right? Remember that?
Oh, yeah, okay.
Yeah. Or if we did sum of this, we've got sum of success. It's a weird thing. We've got this nested structure. What we really want to do is use flat map. Flat map will allow us to operate here on a monad and have a function that can return a monad. And if either of these fails, the whole thing fails. Okay? If either of them fail, the whole thing. If this has failed, it won't even need to apply this function. If this thing fails, it's also going to yield to a value that's a failure. Are we okay with that? We okay? Okay or not? Okay. Okay, so ladies and gentlemen, here this argument to flat map is to indicate what to do with to do next, what to do with the value that's in this monad, right? Or any contained values. What are we going to do with them? What are we going to produce as a result? Okay? And the return value here, and this is not quite right, is a combination of M and really what this should say is F here. It's really this whole thing. We're going to compose, for our case, for Rand, where it's an action, we're going to compose what's going on here with what's being done in the function to get out a combined value. Okay, something that's it's an action that composes both of these. It composes them. This one takes place before that one. Okay, ladies and gentlemen. So here's an example sequencing of computations. We saw this before, and I'd invite you to implement it right now. So I'd like you to import scala.io.underbar. Okay? Import scala.io.underbar. Okay? And now we're going to basically call...
Should we import ST standard in too?
I think this should get all of it there. Let's try it. Okay. So we're going to call readline. Here we are. Okay. I just did readline. This is my input. Okay. Here's readline. We comfortable with that? What does readline return?
Standard in.
Well, yeah, but it returns a string, right? Okay or not? Okay, so ladies and gentlemen, suppose I do readline.toInt. What am I going to get if I type 3?
Here. Oh, it's going to return int.
Return an int of 3. What am I going to get if I type foobar?
It's going to foobar.
Okay, ladies and gentlemen, it throws an exception. See or not? Okay. Ladies and gentlemen, that's something that you don't want to occur in your program. We want to describe a computation that's robust in the context of errors. If we have exceptions being thrown, again, we can write code and sort of wrapped up in complex ways, but it's not referentially transparent. The code is scattered to handle it. We're distracted from the main flow of the computation. And we certainly don't want to do that throughout our data science pipelines. Man, that would be bad. Any point that an error can occur, we have to write exception handlers around it and do weird things. We instead would like a nice composable pipeline, one thing after the other, that flows along. Well, ladies and gentlemen, what could we do to allow this to tolerate errors and basically yield a value? Even in the presence of an error, we can yield a value. What do we wrap it with?
The monad, like try.
Good. Speak on, youth. That's great. That's excellent. That's good. Okay, so we'll wrap it and try. So suppose I type 4, what will I get?
Fine. It'll be success for...
Okay, and what if I type foobar? What do I get?
Failure.
Okay, now is this an exception?
No, it's value.
No, it's a value, ladies and gentlemen. So I could say dot map, whatever this thing is, times 3 or whatever. And if I type 4, what will I get? I'll get success of 12. If I type foobar, what will I get? Just failure. It just propagates it along. It just goes through the pipeline. See or not?
I see where you're going.
It just lets it propagate through it, right? It's a nice thing. Try is a nice thing. It's a lot better than an exception. It may not be obvious when you're doing it with small little tiny example, but once you start stringing into large pipelines, the pipelines needed to perform an HMM,
Oh dear.
or the pipelines needed to compute a naive Bayes model. You don't want to be doing exception handlers all along the way for the various conditions that can occur. Oh, it can occur here, it can occur there, it can occur there. You want to be able to write a nice pipeline and have it, if there's an error, it still propagates through. It's a little bit like what R does with NAs, right? It sort of allows them to propagate through in a nice way without blowing everything up. And with good reason. Okay, ladies and gentlemen, so I could do this, and I could go and flat map and filter it and all these good things, right? I could do filter on this, filter if this thing is greater than 5, and right, do that along. And if I say 3, it's a success. 9. What if I say 1? What will it do? What will it give?
False.
Okay. Predicate. Oh, yeah. Okay. That's mumble. Okay.
What did you give it? What did you type?
I thought I typed 1, but okay. Yeah. Okay. That's mumble. Okay. Let's try doing this. I think I know what's going on. It's a special semantics associated with try. Okay. But let's do this 2 option thing. Okay. Suppose I enter 3. What will it return? Sum of 9. Suppose I enter 1. What will it return? None. Suppose I enter foobar. What will it return? None. Right? With foobar, it doesn't survive. We turned the try into an option. Okay. It turns out, and Winchell would find that interesting. This one, but I'm not going to dwell on it because it takes us off our main focus here. Okay, ladies and gentlemen. Okay, so now we're going to string this together like this. Okay, so we kind of have an understanding of how this is going to work. So now I'd like you to do the following. Try, and it's just going to be what we entered up there. Try of this thing. Dot flat map. And I'm going to say A, resisting impulses in my head otherwise. Okay, and then I'm going to say the same thing here. Watch this. Paste. And I am going to say flat map. And, excuse me, I'm going to say map. And I'm going to say A plus B. Okay, what am I doing? Flat map. Excuse me, what am I doing? Sorry, I'm toning out here. Completely toning out. I'm departing from my script here. Okay, we're going to do this, and we're going to do A plus B. What will I get now? Let's reason this through.
Interesting. If you'll get the quotient unless B is 0, in which case you'll throw an error.
Okay, so ladies and gentlemen, let's reason this through here. So I'm going to flat map on this try, right? Suppose that the try holds a value, a legitimate value. What would this yield? What will A be? Suppose it's try of 3. Will A be? Yeah, and which particular integer? If this is try of 3, what will A be?
3.
A will be 3.
Not sum of 3.
Not sum of 3, but 3. It's the contained value. It's the element of the container. Monads are containers, and that's the element of it. If it's try of 3, it'll be 3, right? Mm-hmm. If this were sum of 2, it would be 2, right? Okay, so this is 3. Okay, now having gotten that 3, what is this going to do?
Reads in another end. To
Well, it reads in another end, and then it's going to perform a map on it. So suppose this A were 3, and suppose this reads in 4. So what is B then?
4.
And what is this?
7.
Indeed. And what would the entire result be?
Sum 7. Success 7.
Or success of 7. Yeah. Okay, so let's try it. Ready?
Sure.
3, 4, success of 7. Now, let's suppose that I were unkind, and I said the first one is foobar. Notice it didn't even ask me for the second one. Why is that?
Because it knew it automatically bombed and failed.
It knew automatically.
One in try.
Yeah, ladies and gentlemen, it got this try.
Mm-hmm.
It was a failure, and FlatMap said, well, on a failure, I don't even need to do what's next. And it just bombed out immediately, right?
Mm-hmm.
It handled this case. It sort of returned the failure. Okay, so let's suppose I were to enter for the first one 3, and the second one I were to say bar. What will happen then?
Same thing. But it'll go all the way through.
Yeah, it'll go all the way to B.
It'll go all the way. It'll try. Okay, it got here, and then it got a failure. What will it do? What will the result of mapping that failure be?
It won't map it, I don't think.
Well, it will call map, and map will say, oh, I have a failure from this function.
Okay.
And what will it return?
Failure.
The same failure. And that failure being returned by map will be returned to FlatMap, which itself will return a failure.
Mm-hmm.
And that's what we see here.
Mm-hmm.
Do you see that?
Yep.
Ladies and gentlemen, so what this is saying is basically do this first, then with the value from that, do this,
Mm-hmm.
and within that, do this first, and when you have a value for that, add these two together. Do you see that?
Yep.
That, ladies and gentlemen, is exactly what this does. Now, this had cruft because I did this. I didn't import it. But what's that? Now, notice that I could also try this. So I used a simpler case here. But suppose we were to try this to be this, ladies and gentlemen. Try of A divided by B. What would happen then? So suppose I did 12 and 3. What would it enter?
Successful.
Success 4.
Success 4.
Okay. Mumble. What do I need?
Flat map.
Indeed. Flat map. Boom.
It's 'cause you
12,
put the try inside the
4.
map, right?
What's that?
Because you put the try inside the map.
I put the try inside there. Yeah, exactly.
Now, with the function you have in the
Yeah.
one slide,
Yeah.
if you put 0 in for B, will that not fail? Because map does not check if the function itself fails.
Say this again.
If you have map of A divided by B,
Yeah.
and you give B as 0, and you're just mapping it over something, won't that throw an error? It won't be caught?
If B is indeed 0, yeah.
But if we put a flat map of the second argument instead of map, it should catch it. If
No.
we do it correctly.
Yeah, because
You just do it again.
I think it'll. It's an interesting question. I think it would cast it to a try,
Okay.
and therefore let's try it, right?
I mean that's what I'm kind of making sure.
Okay, so let's suppose we did this. What I would argue is that because this is a flat map. Okay, so let's do it with map first, right? Here with map, right? Okay, I'm going to enter 3 and 0. What do you think will happen?
It's funny. It's funny.
So it actually returns the failure. Okay.
Oh, you took out.
Took out the try.
Okay. If you put the try in there, you get a success, failure, and then a thing.
Success.
Success, failure, and an error.
You succeeded in producing the error?
That's
Is
right.
what you're saying?
That's right.
Cool.
Yeah. Okay. So, ladies and gentlemen, so this actually does return this. Why?
Well, that's good.
Why is that? It's because the thing that's calling the map is itself a try.
Yeah, so it's returning a try-in, sure.
So it's in fact catching this, returning
Okay.
returning a try.
Fair enough.
So, ladies and gentlemen, suppose you were to do flat map here, and then it needs a try here,
And
right?
you
Yeah.
got there, right.
But in this case, yeah, we'd even need it because the basically this thing around this is expecting. Okay, so this thing here, when you're calling map on it, the result of performing this map is then wrapped in a what? A try. Yeah. So if I do 12 and 3, I'll get successive 4. If I do 4 and 0, I'll get this divide by 0, right?
I can't find a difference actually between using flat map and try or map and no try in this case, because the thing that's calling it is a try.
Correct, because the thing that's calling it is a try,
So it's
I think. I
Completely
think,
the same. It's literally completely equal.
yeah, except in one case, I think the try is being applied at a different place, but yes. I-
Dr. Osgood.
Yes.
My question is this for comprehension the same thing as that? Except that it has to be A divided by B instead of A plus B.
So,
So I can write this bigger if you need it. Like, can I write for A equals read line dot 2 ends, and then B equals read line, we'll tries, you probably do tries, and then just write A plus B or A divided by B. Is that what's going on, or is that what this is?
so
I'm just saying, is it for A equals try of read line?
correct,
And then B
yes.
equals try of read line dot 2 ends, and then just return A plus B, or A divided by B.
A divided by B. Yeah, I mean, basically what you're talking about is
Yeah.
basically this. I
Okay.
I actually had omitted this by accident, but this would be, here we've actually put the try here explicitly. It's a flat map. It's returning a monad, a try, and then this, for whatever value results from this, we're calling it quotient and just returning quotient,
Okay.
right? And that's exactly equivalent to this. So here we're trying to get an n, trying to get this, we're getting the quotient, and we're yielding it.
Okay.
Yeah. Yeah.
Sorry,
Okay.
I was just trying to understand fours. They're very difficult at times.
Yeah, so I have some other slides on that I'll try to show to walk through. But basically, there's a flat map being called on this thing, and the result of that is being called, and each element of that in turn is being called A. So flat map being called internal to that on this, and the result of that is being called B. Flat map try on this, results being called quotient, and then it yields quotient. And that's what you see here. Flat map on the first thing, this is A. Flat map on the second thing, this is the thing that's the element of that here is try. And this last one is actually, I said a flat map, but it's actually a map being called here. The final one is just involves a map on this, and we're calling the value quotient, and then we're returning it. That's what this is. The last one can involve a map because we don't need the further computations to return a monad. It's just returning a value. Okay. So this is flat map. So let's talk about its use here. Okay. A key point of flat map, exactly how monads, and really this again should say, and F are combined to yield the result MB varies from monad to monad. So for rand of A, many other action monads, basically we're composing these. So So if we are calling it on a monad that performs an action, and this is encoding another action of sorts, the results, MB, is just composing these actions. Okay. An option, as we've seen, M on flat map F only calls F if M is some value. If M is none, F is not even called. Right? It doesn't even need to do the next actions. It just bombs out right there. With try, it only calls F if M has succeeded. If M indicates failure, F is not even called. Okay? Okay. And as I say, the semantics of flat map are constrained by the need to adhere to monad laws. Okay, we'll talk about that later. So, ladies and gentlemen, in the chapter, we have here a definition of RAND, and I've tried to place it all in one line, because one of the challenges for me in reading the chapter is that there's kind of scattered code at different places here. So I've tried to put it into one place. The key thing here is that RAND, this random number action, it's a function. This is one challenge that thinks about it. It takes in a random number generator and it returns a value, often the random number you generated, could be a constant, and the random number generator that results. Okay? So if you've generated a random number, will this one be the same as that one? No. If you just have a constant, yeah, this might be the same as that one, right? Okay, now there's some additional items. There's unit. What is unit doing? It's turning a value into an action that takes a random number generator and simply returns that value. Okay?
Pairs it.
Sorry?
It just pairs it.
Just pairs it up with any random number generator you give it. Int here is going to generate a next int, and next int is defined in a way that it returns a value in a random number generator that results. We call it a random number generator, and it returns a pair of these. Non-negative int is something that basically takes a value to determine the next int. You'll notice again, next int returns a pair. If the value is the min value, then we call this recursively. We try again with a new random number generator that resulted from this. Otherwise, it takes the absolute value of it. Okay, so if it's minus 1,000, it gets 1,000. If it's 2, it's 2.
That's funny. The way
Okay.
you have to guard against the minimum value that
Yeah.
you're using.
Yeah. I don't think it's not my preferred example, but it's okay. Okay, now we're going to define map. Okay, here's map. Okay, so map here, now the way this is defined in the book, they're trying to treat it in a little bit more traditional style when they first introduce it. So it actually takes in, just like here, it actually takes in as its first argument, the first parameter lists a monad, this action. Then the second thing it takes in is a function,
Mapping function.
this mapping function, which here takes TDU. Why TDU? Why is this say to M of B, but here we actually just have it going to U? Because it's a map, not a flat map. Flat map is going to take something which produces a rand of U. This produces a U. So we're mapping over this rand a function. Maybe it squares the value, right? And how do we define it? Well, this, remember a rand is a function, so that function takes in a random number generator. And based on that random number generator, RNG1, it, ladies and gentlemen, is going to get a value for this existing action, okay? And that value is going to be passed to f, which is going to map it. Maybe it squares it. And we use the random number generator coming out of this first action. So again, the monad here, this m, this is an action, ladies and gentlemen. It's something that generates, that is potentially generating values from random numbers. So this is a function, and before we can compose it with this one, we basically first evaluate this function, get the return value, and then we pass its return value, v, to this function here, okay? And we return the random number generator, so performed. Okay, now, how is that different from flat map? Well, in both cases, they take an action, and conceptually, that's this m here. Take in an action. Remember, rand is an action. And then they take this takes the next action, which basically takes the results of that action, returns a rand. Okay, so it doesn't merely square it or something like that. It actually may generate random numbers as well. Okay, now let's consider what the resulting value is. So these are two things. This is one action, this is another action, and it's going to compose those actions. How is it going to do that? Well, it's first going to perform the first action, and then it's going to feed the results of the first action to the second action. Notice up here we didn't have to do that. This is just a function that manipulates the value. Here the next action is something that takes the value resulting from the first, but it also takes the random number generator resulting from the first and returns itself a random number generator. Okay, so here flat map is something where we are going to use it to be able to perform an action that can itself generate drawn random numbers. Okay, here this is an action f. Can this action draw on random numbers? No, this is like square a number. Yet all it does is it takes in like an int and returns, maybe it's a double, or maybe it's an int, or whatever. Some other, potentially other type, or it could be the same type. Here, this action takes in an int, but it can, ladies and gentlemen, this action might, in fact, call in a random number function, so it takes in a random number generator and returns a value in a random number generator that results. So this rand of u, remember this is a function. It takes in a random number generator, returns this. And what is the function that's returned? Well, it's whatever function, it's this function right here, which composes them. This composes the two actions. First, it performs the first action. Second, it performs the second action. This action is what comes next, just like we saw here. Whatever's inside the flat map is what comes next after that. We call this thing, this 2int, and with the value that results, we do this here. This is what comes next after we perform this. Do you see that?
But can't you do that with just a map and no try?
Not if the thing that you need to do itself requires random numbers here. Right? Or if the results here, if the thing that you want to do with the number that results in this involves a try, if you did this with map instead of flat map.
No, the second one is a map.
Sorry?
The second one is a map and no inner try.
I mean here. Yeah,
No, the second. That's the third one.
You're saying if you did this,
as a map,
what would happen?
and then you get rid of the inner try. Although I don't know what happens with the map. I don't know, I poke around at it.
Yeah, in general, you might not want that because this might be with a different element type than you get with this or what have you. But yeah, it's an interesting, in this case, it's less sensitive to it. Yeah. But the point is, the reason we want a flat map here is because this thing itself might return a try, might fail.
Mhm.
Remember, we use flat map, ladies and gentlemen. We could use plain old map if the computation here won't fail, right? We can use plain old map here if the computation we want to perform doesn't do what? No, this computation with rand.
It doesn't take a random number.
It doesn't generate, yeah, it doesn't call in random numbers.
Because if we did, then it would mutate the random number generator.
Precisely.
Without the.
That's right. So, ladies and gentlemen, map is used when we want to use a function that doesn't need access to the container, the monad, right? Doesn't need access to try here. What would happen if we did do this, Scott? What would happen if we had flat map A goes to some try expression? What would happen? What would we get out? Sorry, if we had map instead of flat map here.
Try.
We get a try of a try, which is not what we want.
Well, if you, yeah, that would be what you didn't have, you had to have get at the end to get it.
Exactly.
If you want the value.
Yeah, exactly. Okay,
So-
yes.
Okay, so this entire question with rand is making me think of in simulation modeling when you specify the random number generator in your distributions,
Yeah,
so that you can duplicate the results. Because that's there's two reasons to do it: common random number variance reduction, and the ability to. I know exactly what's going to happen because I know that if I give every single source of randomness in my model a different random number generator,
yeah,
then I know exactly I can directly reproduce it by using the same seeds for all the numbers.
sure.
Okay? That sounds similar to what we're doing here because that means, you're not exactly returning the state, you're still guarding against this issue of I don't know what's going on with my random number generators or in general my states.
Well, yeah. I mean, you're making it functional, so it's specified exactly.
Now, in general, if we're looking at let's look at a state chart.
Yeah.
What you're saying is that whenever a transition fires and something happens on that, we also have to return the state it goes to, in addition to the actual action it performs.
So if you want to capture that in a purely functional way, rather than simply modifying behind the scenes the state that this is in, what you would have it do is sort of return the next state.
Right. So instead of
Return the updated state for the agent.
So you could think of it as every time I do something, the state is here, and then I return this state, whatever
Right.
the state is, and then next time do I return this state. So for example, in a Markov model,
Correct.
it's like I'm returning, you are now in state 3 instead of 2 because of whatever fired.
That's right.
And then
Yeah, but in order to do that, one of the key things is
flat map.
from the chapter. Well, there's flat map. Flat map allows you to compose this, but this is a key thing. In order to capture those actions, the monad, the thing that's represented, the rand, the state, those need to represent actions. They're not representing just by itself the state, the value of the state right now at each hop. They're actually representing an action. The monad is representing it's this statement or this state action or this random generator action. So remember, rand of A here is something that takes in a random number generator state and returns a pair of this.
So we're not returning states, we're returning the next transition.
Correct. So the result of applying flat map to such an action, specifying value f, basically composes the earlier action with the new one to form an action that performs both. That sequences them. That's exactly what this does. It's given this action and given this next thing you want to do with the results. Remember, that's what this is.
Right.
This is what you want to do with the result of this A that's captured in here. That's resulting from here. What you want to do with A is represented by this. And similarly, what you want to do with the result of this action is represented by this next action. Here's the result of this first action, and you might want to do something that involves generating a random number with it.
Okay.
And the result of flat mapping that is a composite action that first performs the first one and then performs with the results of the first one. This should actually say, and I stand remiss, I should have caught this. This should actually, hey, come on, hey, get over there. This should actually say V2 here. V2, okay. So the results that came from the first action are then given to the second action, and it returns. What does this return? This next action. It returns a what?
Rand.
Yeah, well, yes. Next action of V2 returns, okay, yeah. So I have to be careful here. Okay, so this is interesting. Right. So next action of V2, that is a rand. You pass it a random number generator, and what does that return?
T-rand pair.
It's a pair of these. And so this overall action, ladies and gentlemen, is going to, and I need to be careful here because this is not what it's saying right now. This needs to actually take in a random number generator like this and then perform that with it. So remember, whatever this returns has got to be a rand of u. And what is a rand of u? Well, it's a function. It takes in a random number generator. That's what this does. And it returns a pair. Whence does that pair come? It comes from this one, this guy here. You first do this one, and then you pass that, the results of that to this one, and this will return, as Kurt observed, the results of calling next action with V2. Next action with V2 is going to be what?
It's a rand, and then you apply random.
Correct. Next action of V2, next action takes a value here, and it returns a rand. And then rand is a function. You give it this, and it returns a pair. Okay? So that's what that does. So ladies and gentlemen, in the example from the book, we had this. This is kind of the crowning achievement of that chapter. What does this do? Well, first we generate a random number here. Where's x coming from?
Generation of the random number.
Well, that was the number generated, assuming, the number generated, that's x.
Okay.
This y is coming from where? This next one that was generated. These x's are coming from what? Well, this is a list of random numbers that are generated of length x. And for each element of the list, we're going to take it mod y. Okay? This whole thing is going to basically, ladies and gentlemen, generate sequences of random length between 0 and some random upper limit. Okay, now, this is what it turns to with the for comprehension, which is
so much better.
It's much cleaner, right? Okay, so we're getting a random.
Somewhere else.
Int is specified
No,
here.
it's-
Int is specified elsewhere in the
Okay,
chapter.
okay.
Yeah. So here we get one random number. Here we get the next random number. Here we generate a set of random numbers of length x, and then we're going to yield, and then for each of them we're going to yield the result of taking it modulo this thing. Okay.
For 30 seconds.
Yeah, sure. Class.
Class dismissed you, right?
Yeah, class
By
dismissed.
the way, it is lunchtime, guys.
It is
Yeah.
Let them
class
hold you
dismissed.
over lunch.
Yeah,
Fair to you guys.
yeah.
Your ERA common account.
Oh, yes. For NIH?
Yeah.
Oh, fun. Okay.
Yeah, I know.
Okay, ladies and gentlemen, that's all for today.
Everyone's been out and busy.
And if anyone wants to talk for office hours, I'm happy to do that after I address this need.
Yes, and well before 1 o'clock because he has a meeting with Dr. Vattenborough at 1.
Oh,
For Marcus Hall.
okay.
Yes.
That's right. I have to go over to Marcus Hall.
Yes, you do.
Okay, thank you.
I have
Thank
to
you.
make sure he gets better.